Okay, so I'll probably have your exams graded by the end of the week. Like, including today's class, we have five classes. I'll do the same as we have done before. So like the last class, which is on a Monday, I'll just turn it into like this office hours kind of thing. So like there will only be four more classes left, including today of like actual material. And we're kind of like getting to we're going to still do more applications, but these like remaining topics are kind of like interesting. Um, because it involves like what's called like integer programming, which is an important subject. So I'll kind of like tell you what that is about all about. Um, and then, but yeah, so like in terms of material, there are only four more classes left, and I'll try to kind of like put on over the weekend, like kind of like the all the problems left for you to work on for, like for the final and all this stuff. Um, oh yeah, sorry. Oh yeah, it will be cumulative. Kind of like the material is very repetitive if you think about it. Like there's not that much stuff. Like many of the like the majority of the problems will be kind of like just setting them up because there's no point in me asking you to do the simplex method three times. You know, if you kind of like know how to do it once, then that's enough. But then I could ask you, set up the if you had wanted to perturb it, you know, the non-degenerate case, what would you have solved? I just wouldn't care more about you solving it. I'll definitely put like a problem which is just like solve something using the simplex method, but I don't see the point in doing that more than once, you know. So and most of them will be similar to also how we did it for this exam, where like just tell me the system of inequalities that you would have solved or whatever, because there's really like the simplex method is just so long and no one ever does that by hand anymore. Like like really like what makes I mean the course is interesting, but what's most interesting is how do you put things so that you can use the simplex method to them. You know, how do you find the inequalities? How do you find all this stuff? Uh, because after that it's just basically, you know, like putting it on the computer. So I will have one kind of like computational in the sense of like I solving it with the simplex method, but the others will be more like how do you set it up, how do you do all this stuff. So but it could be about anything. So how do you set up the degenerate like, you know, write it with the perturbations, or like these problems about is this convex, is this not convex, you know, kind of like. But yeah, there will be but yeah, you should definitely review everything. But there's not, I don't think there's that much. Like this is kind of like a light course in terms of like actual material because it's very repetitive, you know, kind of like always does like over and over the same stuff. But and but yeah, it would be mostly like a setup type exam, you know, like just setting things up. So yeah. Anyone else? Okay, so before I tell you about the integer programming, I'll make a remark, which is useful for all the stuff that we're going to be saying in a moment, but this is in complete generality. Like it has nothing to do with linear optimization. Like it's just like a fact about functions, right? So this is like a fact about functions. Let's say you have two regions. It doesn't have to be in two dimensions or anything. I'll just draw the picture as if it were like in 2D, but so region two, and inside of it, you have region one. Okay, so you have two regions in space, and again, it can be more than two dimensions. You know, any number of dimensions. But the only thing that I am being kind of like accurate in the picture is that one region is completely contained inside the other. So for example, if we were in three dimensions, like you could have like a ball, like and then a smaller ball inside that one, like so or like a cube inside a ball or whatever. But like in the picture, the only thing that you have to worry about is that one region is entirely contained. So I mean, they could be equal, but like then it would just be like the same region. So I do want to think of their as being like a gap of sorts because you'll see what I'm about to ask. Because if they were equal, like it wouldn't be that interesting. We're going to compare like if you had a function, how are the max related inside one region versus the other? So R1 is entirely contained in R2. So let's say that you have a function. So if you have a function f, and let's say that we're in the situation where like the function has like an absolute max in each region, right? Which has an absolute max. Let's call the first max M1 because it's in region one. So maybe this is X1 and this is like the max. I'll think about it as a vector because it could be in high dimensions. So, you know, and then here f of X1 is the max. And then on region one, oops, and an absolute max on region R2. So maybe I don't know, maybe here is the spot where think about it in terms of temperature. I always like to think about these things in terms of temperature. So it could be like the function could represent the temperature, and so you're looking, and this could be like the temperature on a plate. So there's for the smaller plate, the max happens somewhere, the hottest point is somewhere, and then for the larger plate, the max happens somewhere else, right? So, I mean, hopefully this will be kind of plausible, but my claim is that there is a relation between these two maxes in the sense that at least one has to be always larger than the other or larger or equal to the other, right? Like there's kind of like an inequality between the two. I don't know if you can think about which way the inequality should go. Anyone wants to take a guess? What do you think? Yes. Right. Yes. In fact, maybe a better example also is like the solar system. So like M1, think of about M1 as the Earth and M2 as the entire solar system, right? So like the Earth is part of the solar system, so it kind of like fits in our description. But if I asked you what temperature could be larger, the temperature just on the Earth or the temperature on the entire solar system? So the temperature in the entire solar system could be larger because it includes the Earth itself. So of course, like the temperature can only grow, right? There are more points to consider. So that gives a higher chance for the max to increase. So kind of like the rule of thumb to think about. So there are two ways to think about this is that if you enlarge the region, the max can go up, or if you shrink the region, then the max can only decrease. That's kind of like the two, there are equivalent ways of thinking about it, but both are convenient. So the two perspectives and you'll see why that's useful in a moment. But the two perspectives is that if you're looking for the max of a function and you enlarge the region, then the max can increase. Or if you shrink the region, then the max can only decrease. I mean, it could stay the same, but I'm just saying, like, like when I say increase, decrease, I mean with less or equal. So if you increase a region, if you increase the region, the size of the region, the max can increase. Or that's interpretation one. Or if you shrink the region, the max can only decrease. And that's why I said this is completely general. Like, doesn't matter. Doesn't have to do with anything about linear optimization. It's just kind of like basic set stuff. Like, like about what it means to be contained inside like one region. But it is like a useful thing to keep in mind because of what I'm about to say today, which is kind of like a fun topic, as I was saying. Let me just go to my notes. Maybe decrease. Oh my God, yes, thank you. Oops. Yes, yes, yes. Thank you, thank you, thank you. Perfect, thanks.
It's just any, like, if it's talking about both region one and two.
I mean, you could have like like the regions are completely arbitrary. The only condition is that one is entirely inside the other, right? Uh, but yeah, like and again, they can be two-dimensional. They can be in any number of dimensions. I'm just saying, you just take a random shape in whatever number of dimensions, and if you have a larger shape, and the first one is entirely inside of it, then yeah, the max can only increase. So it's about like subsets. Like if you like sets, like if you have thought about sets, if one is a subset of the other, the max can only increase. Is that making sense?
Yeah.
So in fact, it doesn't even have to do with anything about continuum. Like, like the variables could be discrete. It can be in any, like, whatever notion of space you have. Like, it's just like containment. What you like, the only thing you need for this to work is containment. But it's like a useful thing to keep in mind. Okay. Okay. Now, why is that convenient? Because I'll tell you about integer programming. So up to now, we have worked with linear programming, right? So far, the problems we have done are called linear. I mean, sometimes they're called linear programs, like that's kind of like the terminology for it, or like linear optimization. But so far the problems we have solved are called uh, linear programs. That's why if you try to find books about this topic on Amazon, you either have to enter linear optimization or linear programming. Like both names kind of like go hand in hand. Um, Now, what I'm going to tell you about is integer programming. So today, what we're going to talk about is today we will discuss integer programs. So what does it mean to be an integer program? It is kind of going to have the same setup as before. The main difference is that now you will ask the extra requirement that the variables take only integer values. Okay, so the setup will be similar to the one before. But now the variables will also have to be in integers. But now the variable can only take integer values. That's what I mean. Okay, so let me start. Let me start with a very, very baby example, and then we'll kind of like we'll keep increasing the difficulty. So here's an example. And kind of set it up in a way that looks very similar to what we had done before. But like I'll do it in this way. I will do this one very simple one so that like it's more clear what's going on. So let's say you wanted to find the max of x1 plus x2, right? Subject to the usual conditions. So to x1 greater or equal to 0, x2 greater or equal to 0. Then we'll have like our typical constraint, which is you know what? Hmm. Actually, let me put here 2x1. Sorry, 2x2. Okay. Okay. So far, up to now, this looks exactly to the problems, optimization problems we got discussed. Now I'm going to drop the extra conditions. So the extra conditions is that x1 and x2 can only be positive integers, because like the variables, we will always continue them being positive. So now the extra requirement is that um, uh, x1 is an integer and x2 has to be also an integer. And I'll explain why that's kind of like a very natural requirement. But let's just draw out what's going on. So I'm doing something very simple where you can see everything that's happening. So, if you have like this x1 axis, x2 axis, right? Um, like you don't have like this, it just says like the usual stuff that you're working in the first quadrant, right? And x1 plus x2 is kind of like x plus y, right? So if you draw the line, if you draw the line, like x1 plus x2 equals 2.5, right? If you forget about the condition about being integer, right? In the linear optimization problem, like let me draw first like what the region looks like as a linear optimization problem. The feasible region, right, would be this triangle. And we know from linear, like, from the graphical method that the max is supposed to only happen at one of the corners, right? It's a triangle. It has three vertices. The vertices are easy to find, right? A 0, 0. Then what? 2.50, right? And then 0, 2.5. Right? And I mean, because of the function, right? Because of the function, it's like if you evaluate the function at the three vertices, because of these two, it's kind of like easy to see that the winner would be the one that I underlined, that I circled, right? So that should be the vertex that gives you the max. Okay, so this is where the max happens, right? As a linear optimization problem, right? Like this is like the traditional thing, almost like the thing we did on the first day of class, right? So far, so good. Now, and then this is where you have to have like a reality perspective. If you thought of the variables as being kind of like the items that you're producing, like maybe you're producing two types of toys, right? Toy A, toy B. What is the meaning of saying that you're going to produce 2.5 of toys B? There is, not a useful concept to say that you're going to produce like a non-integer amount of toys, right? You cannot sell half a toy. Well, it's kind of like the assumption here, right? So as a mathematical problem, that's totally fine. But as a real world problem, many times like the variables have to be integers because you can only produce a certain amount of units which are discrete, right? Like you cannot produce like again half a car will never sell. You know what I mean? Like so uh that is why you are interested in kind of like adding the extra condition of like uh having the extra condition of the integrality. That's how sometimes it's called. So, but there's no, like, let me put that as a remark. Let's say that they were cars. I don't know. So producing 2.5 cars, has not really, it's not like a useful concept, right? It's not useful. So that max for certain things could be convenient, but for other things, it's like it doesn't give you like interesting information. So what you could like so now let's try to look at the problem. If you add specifically the requirement that the variables have to be integer values, right? Okay, so now let's draw the problem with the requirement of like the variables being integers. Okay, and now let me cheat for a second and go back to GeoGebra, just because GeoGebra is super convenient for this stuff. Let's see. Let's see. Yes.
You can start with 0.5.
Well, yes and okay. Yes and no. Yes for this one, but is it yes for everyone and not for actually that's what makes this interesting, right? I'm starting with the baby example, but yeah, like that's actually like the major question. Can you just drop it? But okay, so let's see what's happening here on GeoGebra. So if you but no, that's kind of like the motivation to have in mind. That's good. Okay, so that's how it looks. And so if you see here, you get like kind of, this is what people sometimes refer to a lattice, which are just like the points whose coordinates are integers. So 0, 0 is in the region, 0, 1 is in the region, 0, 2 is in the region, right? Um, then 1, 0 is in the region, 2, 0 is in the region, right? Then 1, 1 is in the region. And if you kind of work, okay, anything else is outside the region, right? Because if you increase the value for X, then you get to 3, or like you get to 2, and then you get to, yeah, I think this is fine, right? Like, so this is like this, if you add the requirement of integrality, right? Like both coordinates are integers, there's actually only 6 points to look at, right? And then kind of like how we started at the beginning of the course, you can kind of like do like a trial and error type thing and almost like, okay, you have 6 points. Let's just see of the six possibilities, which one is the one that gives you the max value. Okay. And then we can do that. But obviously this is way easier to draw the grid on the lattice, which is how it's called like on GeoGebra, because like everything's done to scale. So you make sure that you're not missing anything out by, just by accident of having like a bad picture. But and then I'll kind of like address your question with another example. But so yeah, in the integer program perspective, for the integer program, if you want, you can draw the same picture. Let me zoom out. Sorry, enlarge it so that it's a bit more clear. You had this line, and so the 6 points that we found were 0, 0, 1, 0, 2, 0, right? And then 0, 1, and then 0, 2, and then 1, 1. So there's like, and that is all. Like there's no space in between those points because like all the other space uses like four values that are not integers, right? So there are only 6 points to look at. So only, okay. And then like, of course, like it's kind of clear, I guess, in this case, what the option, like the answer should be. But if you kind of take the candidate points, and you do x1 plus 2x2, right? I mean, it also won't take that much time to do it, but it's kind of like good to do it at least once. Okay, so you get 0, you get 1, you get 2, you get 2, you get 1 plus 2, which is 3, and then 4, right? So I think those are the values that you get. And yes, in this case, the max of the 6 candidates, right, happens at 0, 2, right? Is that making sense? So far, so good? Everyone with me? So yeah, based on this, and just in this very basic example, it would seem that you just rounded the value, right? How does this compare to the actual max, right? If you had forgotten about like the requirement of being integer values, how does that compare to the actual max? It is kind of like the one that you would get by rounding, right? Like, which is what you were saying. And in fact, it's a little bit smaller because kind of you shrunk the region, right? Like these 6 points are inside the larger region. And so the max can only decrease, which is also what I had said before, right? Like this one had max, the max here would be 5, right? And this one, the max would be 4, right? And so like kind of like the next question is like, does rounding always work, right? That's also something you would like to understand. Okay. And here you have to be careful. It may not be super obvious, but already you have to be careful because, and it's kind of like nice because I chose 2.5, and so the rounding is not obvious. Like, do you round up or down, right? So if you round down, like you get to 0.2, right? But if you round up, you would have gotten to 0.3, which is already outside the allowed region, right? Like because it wouldn't satisfy like the inequalities. So rounding already in this very simple example, depending on how you round, you could kind of like be taken outside the region, right? So there you like you have to be careful. But it's even worse than that. So um let me do this other example. Example 2. I'll just write X and Y. And again, as always, like the variables will be greater or equal to 0. Okay. And then the variables will be like integers, as which is like the new condition. So maybe I should put that. I'll kind of like put that and like underlined it to emphasize that now that's a main difference to what we're doing. Okay, so just as before, you could kind of like just forget about that for a moment, which by the way, I will call that in a moment a relaxation. So that's what you call like relaxing the problem where you just kind of like forget about certain conditions. So relaxing this problem is just like, oh, let's just pretend that the variables were not integers so that we can treat that as like a regular problem. So if you, let's just go back to GeoGebra. I feel I should just restart this. Okay, so if you go back to GeoGebra, so you get 2x plus 5y less than 71. Okay, oops. Okay, let's zoom out here. And then the other inequality was x plus 3y greater or equal to 30. Well, that's greater than 30 just works. Okay, so these are the, this is, of course, you're just looking at the region, on the first quadrant. So it's kind of like this, not rectangular strip, but it's almost like a rectangle, right? The lines are not parallel, so, but it's like a quadrilateral, right? Like what you get there. Okay, so in this case, there's like a corner here, right? There's a corner here, there's a corner here, and there's a corner here, right? So there would be 4 points to look at for the max. Um, and you can kind of like check for like the function that I wrote that the max would be at kind of like this corner because the y value was being multiplied by 250. So that kind of like wins like at the end of the day. So the max happens to be at 0, and I think that should be what 14. It's kind of roughly 14.2. Okay, so that is where like the original max would be, and like actually let me write that as I'll kind of write this in on the iPad in a moment. So, but what I'm saying is that if you forget about um again, if you forget, let's put it here. If you forget about the variables being integers, like the max would be at x equals 0, y equals 14.2, and the max was would be 100x plus 250y. By the way, I would let you bring a calculator for this exam. I mean, not the end of the world, but like the fractions are kind of like annoying, so I don't mind if you bring one, just to compute these things, like so and then okay, 250 times 14.2, I don't know, but it is 3550 if I'm not mistaken. Let me double check. Yes. So the max here will be 3,550. Okay, perfect. If you round, for example, like as you had like mentioned before, right? The only obvious rounding here would be 14.2 to 14, right? So the rounding option, right, would be 0.14. Okay. Okay. So that's perfect because it does land in the feasible region, meaning that it does satisfy the inequalities. Okay, so the rounding, which is x equals 0, y equals 14, right? If you put 100 zeros, 100 times 0 plus 250 times 14, okay, definitely the max drops a little bit. And I think it just gives you 3,500, if I'm not mistaken. You can double check on your calculator if someone is playing with the number. Okay, but my claim is that if you choose, where are you? 3 comma 13. Where are you? Oh, there you are. Okay. If I choose the point 3 comma 13. Okay, this is both have integer values. So this is one integer solution, right? It's in the allowed region, right? Because it got colored twice. If you choose 3 comma 13, that gives you 3550. So it actually gives you better answer than the rounding, right? So, so if you choose x equals 3 and y equals 13, the important thing of this example is that it is better than the rounding. So, and this is already like a very basic thing because it's only in 2 dimensions. So already in 2 dimensions, you round and you don't necessarily get the best result, right? And that's kind of like what you should have in mind, that it is really like a completely different problem. Finding the integer values that give you the largest amount has maybe completely, I mean, like it's not easy to predict this value based on the max, you know what I mean? Like the actual max to the original problem without like that integrality constraints. So the kind of like the moral of this example is that rounding can completely be it's like 100% misleading. Like it may not be like what you actually look for in like these problems. Um, so let me just write that down. Yeah.
The max isn't always going to be.
Yeah. Well, right, exactly, but also even more because first because in integer programming, like that's a good yes, that's let me just write this down and then I'll answer your question, but that is correct what you just said. Um, so like, what I was saying is like without asking for x, y to be integers, the max happens to be x equals 0, y equals 14.2, right? And the max in this case is 3550. The rounding would be x equals 0, y equals 14, and the max for the, I mean, not the max, I should just say the value, because it's not going to be a max of any sort. So the value is just 3500. And if the actual max for just like looking at integers, the integers, like the actual max, if you restrict yourself to integers, is x equals 13, y equals x equals 3, y equals 13, which in this case gives you uh 3550 again. So rounding can not be optimal. So the point of this example is that rounding may not be optimal. Okay. Now to your question, like it's even worse because in integer programming, since like the coordinates have both to be integers, you just get like a finite number of points, right? And that's completely discrete. So there's not like a sense in which you can talk about corners, right? I mean, because there's just a bunch of points scattered on the lattice, right? In fact, like actually, this is like also another cute animation before continuing to discuss what to do. Um, where do I have this? I think it's called Pick's theorem. No, sorry. Yeah, these are very cute animations. I hate their search bar definitely needs to be improved because if you put an apostrophe, it goes from zero solutions in the search engine to all these options. So they do have to, but I do like GeoGebra a lot, except for that. So like yeah, what I like about these animations is you can just kind of change the inequalities and you see how the lattice points change. So the lattice points, I mean, are the green ones. Like there could be some on the boundary, but they're just these are like the green points are the ones that have integer coordinates, right? But if you like, and so again, like even need to be convex. Like in this case, like in this animation, let me put something that does look convex. Um, like I mean, but it is just like a bunch of points. Like it's not like super obvious in what sense. Like one like even this makes it a bit more clear. It's not super obvious in what sense. Like some of these points would be like corners of others because it's just like kind of like they're scattered, right? Like I mean, they're always like one unit apart, like horizontally and vertically because they're like integer lattices, but it's kind of like a crystal, right? But yeah, why would a point it's not clear why there's no almost no geometry here because they're just like a finite number of points like that you scatter on the plane, right? So referring to a point like as a corner or something like that, it wouldn't be like appropriate in this context because there's no solid, there's no solid region that you are talking about when it's just like integer solutions, right? Is that making sense? Of course, there is a trick that does will allow us to turn the integer program into a linear program. Otherwise, we wouldn't be bringing it up in this class. But I'm just saying is that there is something that needs to be done because, like, the difference can be drastic. That's what I'm trying to show you. It's like, you do have to, like, it's like a clever solution, but like, something has to happen because rounding is not necessarily the best solution, like in general. Um, But this is important, as I was saying, because, and in fact, like the most common use of linear programs is to solve integer programs, because you only want, in most cases, integer solutions. Like again, like if you're like a supermarket supply chains, you have to decide how many. If you're like Amazon, you are trying to decide how many. How do you choose like the routes to transport like the products or like the what you're selling. You cannot just like ship half a box of some product. Like no one would uh, like accept that. So most of like the like linear programs in practice are used to solve integer programs. Also I mean, I'll see how much time we have with those, just like the four classes. But also integer programs, another good cool application of integer programs is that if you take the variables to be 0 or 1, then that is binary. So you can use that to like model like situations like what people call like propositions in logic, kind of so it has like connections to like programming in the sense of computer science, because like you can represent 0 as false and true as 1. So you can have a bunch of variables which are called binary variables, and then you can use this decision trees and other things to do these things. But yeah, if we have time, I may tell you how to apply this to binary situations. But anyways, what I'm trying to say is that the important thing of this example is that rounding sometimes seems to work, but other times does not work. Okay, so now I'm going to explain to you how are we going to solve this using like a linear program, and you'll see it's like a very clever solution. Okay, so now, so how are we going to solve? Put this, see. Ah, here you are. Yeah. These problems, the integer programs. So we're going to do a technique which is called like a branch and bound. So we'll do something called the branch and bound method. Okay. So so how does this look? The idea, let me show you how it works on a concrete problem, because once you understand it on a particular example, it's always easy to know what to do. So let's say I wanted to solve this problem. Well, sorry, as always, like the variables are non-negative. And then I'll put this. And then the new requirement is that x1 and x2 should be integers. Okay. So the branch of bound method, what it does is like step one, you just solve the problem for getting the requirement of the variables being integers. So you just solve the traditional problem that we know how to solve from day one, right? So okay, step one is to solve the ordinary problem by dropping the requirement on the variables being integers. So solve the problem by dropping the integrality requirement, the integrality requirement. So this is called like a relaxation because you are relaxing the problem. You're making it easier, right? Like kind of like relaxing it is kind of like you're less stressed. So, you know, like there are fewer things that you have to worry about before, because with you, if you ask the variables to be integers, like that is extra stuff to be concerned about. So this is sometimes called like a relaxation of the problem. Is that making sense? Like the terminology. So whenever you relax the problem, the way to think about it is that you make it easier to solve. That's kind of like the philosophy to have in mind. Um, in fact, if you read the book, like again, I do like the book a lot because it does give a lot of like discussion about like how this is related to computer science. Like these integer program problems are kind of like those which are called like NP hard. So which is like kind of like a terminology in computer science for like the complexity of a like whether like a problem takes polynomial time to solve and like kind of like this stuff about like algorithms. So if someone is interested, you can read like the book, like chapter 3 is where like they discuss this stuff and they have these conversations. But the idea is like basically integer programs are really hard to solve in general because if you can take the variables to be 0, 1, then you're taking the binary variable. So basically every program, like any almost like problem involving propositions, like in computer science could be represented like, in a sense like by one of these problems. So I actually made I'll kind of like show you first like with the animation what's the method is supposed to work, and then I'll kind of like write the steps on the board. But I kind of like did it on GeoGebra before coming to class so that we could just kind of like see it because it's very natural. So like understanding from the picture is kind of like easier. And I put it online so that you can kind of like play with it if you want. So you just have to enter branch and bound. Let me see if like that's how it should be. No, branch. Let's see, Mariano Echeverria. Ha, perfect. Here I am. So you just enter branch and my name, and then you'll find the activity. So let's see if I can. Okay. I'll explain in a moment all that you're going to see. Let's see. Uh, let's see. Triangle, and then there's this other triangle. Okay, perfect. So this is the original region where if you forget about the variables being integers, if you saw I wrote 3 inequalities, right? So like one inequality is this one, the other inequality is this one, the other inequality is this one. So you get like kind of like this funny looking region. Okay. That is if you forget about the variables being integers, that is where you're trying to find the max and min. Kind of like the way I chose things is, I mean, I chose like an optimization problem, which is easy because like the function that we're optimizing is just x1 plus x2. So you just have to add the coordinates, you know, to find the max. So, I mean, in this case, it's not too like there are only four vertices that you would need to look at this one, and that one, and it's kind of clear that the top one is where the max happens because like the function is just like the sum of the two coordinates. Is that making sense? Um, I believe I kind of put it is a yeah. Okay. Okay. So that is where the max to the original problem occurs. Okay. And then okay, so now comes the next step. If you look at the coordinates of this point, both are not integers, right? Both are not integers. So kind of what you do, and this is where like the branching comes in. We're kind of like going to break the problem into two, okay? So, and like the way I mean, obviously, if you care about efficiency, there are better ways to do this. But what I'm going to do is kind of like focus on one of the two coordinates. Okay, so for example, let's focus on the first one. So what I'm going to do is add an as extra conditions. I kind of like the alternative to rounding this up is just to say, okay, if this is 2.767, if you're looking for like integer solutions, I'll kind of want to find like an integer solution that's close to this one, right? But the way I'll do it is kind of like adding as extra constraints, kind of like that x should be less than 2 or that x should be less greater than 3. So I kind of like I'll move, you know, x less than 2 would be this extra constraint, and y x greater than 3 would be that extra constraint. Because there won't be any integer solution in this strip, right? Because in this strip, the x value is between 2 and 3. So you cannot find an integer solution here. Is that making sense? So kind of like the next best thing you can do is like less than 2 or greater than 3. Is that making sense? And what that does, and you see like it branches into two regions, right? Which are smaller regions of the original problem, right? So what you do is kind of regard, what I'm going to do is going to try to find the max. Where do I put this here? So what you end up doing is trying to find the max. Where is my other quadrilla? Huh. And okay, so just to go back for a second. So again, if you had the purple region, if you have like these two extra constraints, that x is less than 2 or 1 or x greater than 3, that kind of breaks like this quadrilateral into two pieces, right? So I'll forget about the original region, and then I'll just focus on these two smaller regions. Okay? Is that making sense? So these are two smaller regions inside the bigger region, right? And so this goes back to what I said at the beginning of the conversation in class. Since these are smaller regions, I'm shrunk the region so the max can only shrink, or it could stay the same, but the max will decrease. Okay? So then I'll treat each of these as a separate optimization problem. This is one region, this is another region. I'll try to find the max for each of these separately. Okay. So for example, again, it's kind of like not too hard to see where the max should be because the max is like the sum of the coordinates, right? So if you forget about the integrality requirement, the max like should be here and here, right? Like those like should be the two maxes. You see here. Okay. And this is great because now of the two candidates, right? You know, you have two candidates, right? Both of them have an integer first coordinate, but the y coordinate is bad for the two of them, right? So now that has to be fixed, right? But of the two, right, which of the two has like a better max? The one on the right side, because again, like the max is just the sum of the two values. So of the two maxes, this one is the larger one, right? And so that means that you can kind of forget about the first region because the max can only decrease going forward here. So you always want to keep kind of like the largest of the two. So I don't care about like, I'll kind of like, let me delete this quadrilateral. I don't care about it anymore because this one has a better max. And again, the max can only shrink. That's what is important to remember of this method. So once the max, see, now the problem is kind of like, we're looking in here. And so I'm going to do another branching. Okay. So because it's a 3.5, what I would like to look is at the points which are below, like, I kind of want to take the strip between 3 and 4. Okay. And did I put so you're looking at the points. When did I do this? What did okay, so why did I do this here? Oh, I think I colored the wrong let me see. Yeah, I colored the wrong triangle here. Oh my God. Let me see if I can, because oh my God, sorry about that. If I look at the region, right, I'll fix it on the notes. I should fix this here. But like you want to take this strip out, right? So you have to look at the stuff above 4 or below 3, right? And below 3 gives you kind of like the stuff, not the triangle, like this stuff. And then above 4, there's nothing to consider because that's outside the region to begin with. Okay. And what you will find there is that the max happens right here. Okay. But that one is already fine because that one has like two integer values. So the only thing in this picture is that I colored the wrong region. I should have colored like uh, this other part. So kind of like in the region, actually, it should be like this like without the triangle. But is that making sense? Like, like the method? Because you always kind of like you break the problem into two pieces and you kind of keep the branch that has like the larger value for the region. Okay, so let me see if I can draw. Yeah, and I'll re-upload this to GeoGebra so that it has like the correct triangle. Let me see if I can find, actually, I probably have the file somewhere in here. Ah, here you are. Yeah. So like I should delete this one. Yeah, so really what I should have colored, sorry about that. What I'm, okay, I have to zoom in a little bit here because this is a bit bad. I think now that kind of looks decent enough. So yeah, I colored the wrong region in the branch and bound just to share it again. So yeah, I will re-upload this to GeoGebra so that it looks better. But what I was trying to say, just to kind of like repeat this, like now with the correct diagram in mind, is that let's see that yeah, we kept you for yeah, you were okay, let's see. And then, and then okay. Okay. So the idea is that, and then let's drop MN and that does play no role. So what I was saying, yeah, like not just to repeat like this, what I was saying is that you focus on this max, right? But this max has Y value 3.5. So all this strip between 3 and 4 is problematic because there the Y value would not be an integer. So you kind of drop that. So you consider the stuff with Y value bigger than 4, which there's nothing that gives you, or the stuff with Y value less than 3, which gives you this region. And there, the corner, you know, as a regular optimization problem, because you want this like integral requirement, like, it's not hard to see, like, because it's just like the sum of the coordinates that the the solution that works is like this corner that I had shown a bit earlier. So yeah, this is such a, I'll fix this in once I re-upload it to GeoGebra. I just want this to kind of like disappear so that it's easier to see for you. Okay. So you kind of like forget about the triangle and then the max happened here. Okay. So if you see kind of like the purple point was the original max. then you get two potential maxes. Neither satisfies the integral condition. You keep the largest max because the maxes can only shrink as you shrink the region. So you kind of keep on the branch that's the largest value. And then you branch again, and then you keep like the biggest solution. But the idea is that at every point, you kind of forget about the integral requirement, and then you just have like the optimization problem, you know, as it's supposed to be. As yeah, so where were you going to?
Okay, so we have the original one, which has both like non-integer x and y.
Right.
And so what we do is we kind of restrict it to the integer solutions that's not between that's 2 and 3.
Yes.
And then from there we solve it again.
Yes.
That time the y value doesn't have.
Correct.
So that's why we reduce it down to 3.
Correct. Correct. Yes. Exactly. Yes. Yeah.
Like any situation where you know how we like disregarded the left side
Mhm.
because it was smaller, that like since both of them are decimals and we want to go like one more level deeper, is there a chance that like the left side next level is a greater max than the right side next level?
Well, that's a good question. Let's see. So yeah, like the way this method works, it doesn't guarantee I mean, this method does not guarantee that you're finding the best solution in the integer solution. It just current, you know, it so kind of like this produces what you would call like a local max instead of like an absolute max, because I suppose it could be what you said happens where like, you know, maybe right, like if both had to be dropping, it could be the case that the drop in this one is smaller in the next step than the drop on that one, right? And so I guess by accident, this other one ends up being like smaller than the other one. But so no, that's a good observation. But the method is a lot less ambitious for this case. So it's kind of more like the thing is like if you kept both, okay, this is where you have to think as a programmer, because imagine you want to keep track of all the branches. Every time you make a branch, you duplicate the number, and then this would grow exponentially, right? You want to run away from exponential stuff as much as you can, right? So theoretically, yeah, what you're saying could happen, right? Where maybe like this other branch could have ended up and then up with a better value, right? Because the drop was less. But if you wanted to keep track of every single possibility, then you get into exponential terrain, and you don't want to do that. So it is kind of like reasonable to kind of just keep up whenever you have two possibilities to keep the one that lowered the least without any guarantees that that was optimal along the way in the totality, you know, of branches, if that makes sense. But yeah, you know, I know this problem because of course, like, you know, it's kind of like the same question, like, why don't you just like evaluate the function at all the integer points? The thing is like, that is a like, you know, the number of integer points in like in a region will grow exponentially, you know, it's kind of like, so like the thing is like you want to kind of like keep the problem into being continue to be feasible, if that makes sense. Feasible in the sense of like realistic that a computer program could solve it. So if you every time you branch, you kind of have to keep keeping track of all the branches, then you're done. Like this is game over. Like you would never end, you know, because then it kind of bifurcates. So it wouldn't be like a practical thing to do. Is that making sense? So yeah, so this will produce but that's a good observation. So this will produce what you would call kind of like a local max in within the branch, kind of like the best solution, but not necessarily like the optimal solution. In fact, um, and then there are like algorithms to kind of like because here's another thing we could have said, like I branch on X first, right? If you remember how the problem started, let me put like the original. I'll probably write this down next time in details because like we're almost done out of time, so I don't want to rush too much. But it's kind of I just want us to understand the picture today. You know, if the way I did the branching was on X first, right? I branch X less than 2 or X greater than 3. Who is to say that if you had branched first on Y, maybe I could have branched first on Y. Like I guess in this case it does produce the same solution, but like maybe if you branch in different order the variables, you just don't end up in the same spot, right? And that is very plausible because we're only keep track of like one branch at a time. You know what I mean? So there you get into the question of like, oh, how do you actually choose like the best like like more like a question of optimality, like how do you choose like of your branches the best situation. Here I'm kind of like just doing it kind of like by a simple rule, like okay, like you arbitrarily branch if there are multiple choices, let's just branch the first variable like alphabetically, and then let's just keep the branch that gives you the lowest decrease in the max. But no, but there's like an entire industry of like choosing better strategies to branch and what to choose or what not to choose, because that is really important to kind of like try to make the drop as little as possible, if that makes sense. So, but we won't get into all those details because it's like a little bit too much of a detail. It's kind of like more like understanding the big picture of like how you're narrowing down like the search space, So you always are solving like an optimization problem, but you're just shrinking. We will keep shrinking the region where you're looking for the max until you kind of like force it to become like an integer solution. Um, but I mean, but it's like an interesting situation. So because it has like many applications. So next time, okay, so next time I'll write this down, like like the actual steps. But I think now that you saw it, you kind of get the idea. Next time I'll also give you this application, which is really cool, which is like say, which is called like perfect bipartite graphs. It's like a perfect matching problem. So let's say I have three people, and like just to make it like even more, like I have 10 people and then I have 10 products I could sell, and every person must buy me a product, right? um and I ask everyone for how much are they willing to pay for that particular product, right? So it could be 10 books if you want it. I have 10 books by 10 different authors. Everyone will get at the end, like will everyone has to buy a book, but you will tell me your preferences. So maybe for someone for book one wants to pay a $50, and for book two $30, and then $0 for the next eight ones. And everyone can give me different collections. And so the problem, as you can imagine where I'm going, is like, how can I sell like the books to my customers so that I end up making the most amount of money, right? So it's a perfect matching because every book has to go to someone. And if you just think about it in terms of like the combinatorics, it would be a gigantic problem because it will involve factorials and a bunch of other stuff. But there's like a very elegant way to solve this as an integer program. It's kind of like clever to see there. And in that case, the cool thing is that the solution that you get by relaxing is can always be made so that it matches like the actual value with the integer constraints. So like there's no loss in the max. It's like one of the few cases where the max actually coincides with or without the integrality constraints. But I'll tell you about that one next time because it's like a very cool application. And so that's kind of like the type of problems that I will ask you. Like I'll give you like a graph. It's like a graph. You can give it in terms of a graph. And then I'll give you this graph with the weights for the edges. This is how you would call it because that's kind of like the amount of money you're willing to pay for the product. So write that into your program that you would like to solve to maximize the cost, like the profit, let's say. But I'll write that down next time, and I'll also write that down like the steps next time, and I'll fix the animation and GeoGebra because yeah, I had missed um, drawn incorrectly that one. But let's end here. I think this is a good place to end.